Okay, continue it.
Formula, then that should be 4.5 times 10 to the 6 Newton per Coulomb. Now let's take a look at the field on position B. So just like the one at position A, the electric field from Q1 at position B is now that is same as K times Q over R squared. So basically, EB1 and EB2 is 8.99 times 10 to the 6, 10 to 9 Newton square meter or square Coulomb times Q value is the charge is 50 microcoulomb, so it is 50 times 10 to the 6 Coulomb, and distance from this Q1 to the position B is the same, so that should be 0.4 meter squared. So the straight line from Q1 to B and Q2 to the B are same. All right, they're this straight the distance from the Q1 and Q2 to B are all same. So that is 0.4 meter. So that leads to the result of electric field out of two charges, which is 2.8 times 10 to the 6 Newton per Coulomb. So now from this EB1. So from this two electric field, you can actually estimate the total electric field out of these two charges on the position B, which is B and EB1. Oh, so actually, total electric field is 2 EB1 cosine theta. So now that is 2 times 2.8 times 10 to the 6 Newton per Coulomb times 0.65. And because of that, your total electric field at position B is 3.6 times 10 to the 6 Newton per Coulomb.
Okay. Does it make sense, or do you have any question?
I don't understand like the very last part, where it's EB or 2 EB cosine theta. Because because they're basically the same electric field from both sides, so the x directions would cancel, and then you would have double the y directions. So wouldn't it be 2 EB sine theta?
No, actually, there's only x component because you see that the Q1 is minus charge, right? So that actually have downward electric field, and this one Q2 is plus 50 microcoulomb plus charge that produce outward the electric field, but their distance between this Q1 and the B and the Q2 and B are same. So their magnitude itself, they're same, but their direction is quite opposite. So if you decompose EB1 and EB2 in XY direction, then EB1X is projected onto the x-axis, and EB2 also projected onto the x-axis. Their actually magnitude is double. But if you projected this EB1, EB2 in the y vertical direction, their y component is actually quite in like their opposite direction. So they cancel each other.
Yeah, that makes sense.
So only leave the x component. So that's why I double this EB1 cosine theta, because you have two electric field add onto each other in the x-axis. Okay.
Mhm.
Does it make sense, right?
Yeah.
Okay. Any other question regarding this? So you may have like all kind of like problems with a similar setup in the chapter this first chapter and second chapter. So it is pretty much represent similar cases of the problem. So let's look at the other sample problem from different textbook. So okay.
So sample problem 22.01. Net electric field. Figure 22-7a shows three particles where the charge is Q1, is 2Q, and Q2 is -2Q, and the Q3 has -4Q. Each distance d from the origin. What net electric field is? Electric field E is produced at the origin. So now you have three charges here, here, and here. And we want to estimate the net electric field out of these three charges on the origin. All right. So basically, you can start with the electric field out of the Q1. So that is E1, which is 1/4 pi epsilon naught times Q1/d squared. So straight distance from Q1 to the origin is d. So now Q1 is plus 2Q, so you can replace Q1 with the 2Q. So that is 1/4 pi epsilon naught times 2Q over d squared. That is the electric field from the Q1 at the origin. And now we want to estimate the electric field from Q2. Same thing. We just estimate field using Coulomb's law. Same thing now is Q1/4 pi epsilon naught Q2 over d squared. So here the Q2 is the same, but the negative sign minus 2Q. So magnitude itself is 2Q, basically 1/4 pi epsilon times 2Q over d squared. And Q3 is same. Q3 with the same Coulomb's law, you just apply. So Q3 is 1/4 pi epsilon naught or Q over d squared. So the first step, you gotta just find out the direction of electric field and then add the field in the same direction, and then just take a look at the total electric field out of three vectors. So if you add three vectors in the same figure, it should be like this. The electric field from the charge Q3 that is pointing in this direction, that is E3 from the charge Q3. And the two field from Q1 and the Q2 pointing in the same direction, because Q1 is positive charge, so that if you look at the electric field at the origin, then that should be this direction. And Q2 is negative charge, so the electric field also pointing the same direction. So that should be this. This one is Q1 from the Q1, and the other one is from Q2. So there are three electric fields aligned in the same direction, electric E1 and E2. So what you need to do is just add these two fields together because they are pointing in the same direction. And then you add resulting field vector with the E3. So you do that, then that should be like this. This is E3, and you have new vector E1 plus E2. The angle is 30 degree, and angle to E1 plus E2 also 30 degree, but negative sign. So first of all, you will have to add two field from charge Q1 and Q2. So that is 104 pi epsilon naught times 4Q or D squared. That is same as E3. Magnitude itself same as E3. So your total electric field should be twice of E3 X component. So if you look at this electric field, they're pointing opposite direction with the same angle. So as you can see, E3 pointing upward with 30 degree, and the E1 plus E2 vectors pointing downward, but with the same angle, 30 degree. So the resulting vector out of those two vectors, this one and this one, should be aligned in the x axis. So there's no y components. All we need to actually just estimate x component of these two vectors and add them together. So that should be E twice of the electric field of E3 times cosine 30 degree. So that is 1 twice of the 1/4 epsilon and pi epsilon times 4Q over E squared. So, and then cosine 30 degree. And that is 6.93 Q over 4 pi epsilon naught and D squared.
Okay, that's the answer for this sample problem. So I think this is pretty much same as the one we looked through the before. You have to just add the two vectors together first because they're pointing in the same direction. So that's create the resulting vector out of two charges. But fortunately, that vector resulting vector out of two vectors in the same magnitude, but they are pointing the opposite direction in y-axis. So there's no y component, but only lead to the x component out of three vectors. Okay, so that circumstance of this vectorial summation is pretty much same as the one we had before in previous example. Does it make sense?
Yeah, but also for the electric field of 1 plus electric field of 2,
Mm-hmm.
I know like because they have two, you could add them together and it'll be
Mm-hmm.
4 and it cancel and it like matches with electric field 3.
Mm-hmm.
But for electric field 1 and 2, isn't it two different signs? So oh wait, actually, never mind. They go in the same direction.
Yes,
So
yes, yes. So they actually that Q1 and Q2 they sit on the straight line crossing the origin. So if you're sitting on the like middle of actually XY axis, they are looking at the field from Q1 is the probably positive X direction, and the one from the Q2 is same direction, is positive X direction. But they align in the same straight line between those two charges. Okay,
mhm.
so that's just double the actual electric field out of two charges, but that's magnitude of the two vectorial summation is the same as the the vector from the electric field from the Q3, but that's pointing in the opposite direction in y-axis. So that's why you don't have actually y component of resulting vector, only lead to the positive x component, but that's double.
Mhm.
Does it make sense, right?
Yeah.
Okay, we have two more example problems today, so let's quickly go over it, and then next week I will start next chapter, the Gauss law and flux of the electric field. All right, let me show you that next problem.
Now let's take a look at the sample problem 22.03. So the figure 22-13a shows plastic rod with a uniform charge minus q. This bent in a 120-degree circular arc of radius r and symmetrically placed across an x-axis with the origin at the center of curvature P of the rod. In terms of the Q and R, what is the electric field E due to the rod at point P? So you're sitting on the observation point P, and there's plastic rod with a charge minus Q. This arc has the 120-degree circumference along the circumference. This 120 degree extends from 0 to 120 degree along this circumference of this arc. So we want to actually estimate the electric field exerted by this arc line charge onto this observation point P origin. So let's take a look. So first step is we gotta just estimate the charge element first. So charge elements of this arc is dq, which is the charge density lambda times the length of small line element in this line charge ds. So that should be like this. The line that the density, charge density on this line charge is lambda, and we are looking at electric field from this small line segments ds. So the total charge should be lambda times ds. The fractional charge out of this arc. So total charge is minus q. So if you integrate this dq along this arc, that should be minus q. The next second. Now we want to just set up the equation of element fields from this line elements. That is dE, the field from this line element. So that is 1 over 4 epsilon naught times dq over r squared. Now you want to replace this dq with the lambda ds. That is 1 over 4 pi epsilon lambda ds over r squared. So now we're going to sum them up along this arc. So the next step is summing of this line element along the x-axis. So you have electric field from minus 60 degree. This is like the charge line element of charge from minus 60 degree to the plus 60 degree. But let's take a look at the x component of electric field of this line charge. So that is the Ex, which is d times electric field cosine theta. That from the number 2, that should be 1 over 4 pi epsilon naught lambda r squared cosine theta ds. So next step, you just replace ds with the angle. So as you know, circumference is radius times theta. So here the s and the theta is, they are all just variable. So if you take a derivative of this equation, then that should be ds equals r d theta, because r is constant value. So
Wait, hello?
Were you disconnected?
Oh, my computer died, so I had to plug it.
Okay, no worry. I'll just replay it and no worry about it. You have 10 more minutes, then I can finish up the problem. We can
Yeah.
just like move on to the next week. All right. Let me quickly just save that video file. And I just FYI, once I finish this session, I will upload today's video in your account. You can just review it and when you need it. Okay.
Mhm.
All right. Let me save. Where should I? Okay, right there. Okay. Reduce. All right. Then there should be some. Got it. Okay, cool. Okay, let me do you see my screen still or
Yeah.
okay, so then I'll replay it. How far have you watched? Let me just take back a little bit.
Mhm.
so yes. So next step, you just replace ds with the angle. So as you know, circumference is radius times theta. So here the s and the theta is, they are all just variable. So if you take a derivative of this equation, then that should be ds equals r d theta, because r is constant value. So that can be out of derivative. So if you replace ds with this r theta, r d theta, then the electric field should be integral of d ex. So you want to estimate now the electric field out of this total line charge from minus 60 degree to the 60 degree. That is lambda. Oh, 1 second. So that is integral from minus 60 degree to the 60 degree, and the 1 over 4 pi epsilon naught lambda r squared cosine theta d are all d theta. Now you can take all the constant value out of this integral, only leave variable which is theta into this integral. So take that constant value out of this integral, that should be lambda over 4 pi epsilon naught r, because the r is cancelled from numerator and denominator, only leaves r on denominator. So that changes the equation from integral from the minus 60 to the 60 degree, and cosine theta and d theta. So here this one is integral of cosine is the sine theta. So now this equation could be replaced with this sine function, which is sine theta from minus 60 degree to the 60 degree. 60 degree same as pi over 3. So this one sine pi over 3 minus sine minus pi over 3. So that is result in lambda over 4 pi epsilon naught r sine pi over 3 minus sine minus pi over 3. So that is same as 2 times sine pi over 3, and this one is square root 3 over 2. So that is same as this one is just square root of 3. So if you add that together, then that should be 1.37 times the lambda over 4 pi epsilon naught r. So that is just the electric field magnitude applied to the origin of P with the distance r from this arc shape of line charge. Okay, so now you want now just to change that the lambda with the total charge, because the lambda is just alternating variable to drive this formula. So lambda could be expressed with the Q, total charge Q. So that lambda is the charge density. So that means you divide the total charge by length of the arc, then that should be the value of this line charge density. So then total charge Q, and then the length of this arc is 4 pi r over 3. So that is 0.477 Q over r. Let's replace lambda with this. Then electric field, total electric field E should be 1.37 times 0.477 Q 4 pi epsilon r squared, right? Now you just replace this lambda with this result, and that electric field like this. So basically, if you just multiply 1.37 to the 0.477, then the total electric field component in vectorial space is the electric field equals 0.834 pi epsilon r squared Q. Well, here then that is unit vector I. So because just like the previous problem, the symmetric line charge sitting on x-axis, and all the electric field from individual line elements create the two vector component along the x-axis and the y-axis. But if you look at the two line elements right there and right here, and if you decompose that electric field component, so basically that will be one from this line element, create the electric field is downward, and probably, I'm sorry, this direction. And the other one should be this direction, right? Because negative charge, the field probably just inward to the line charge. But if you decompose this electric field that have this component on x-axis and the y component, and this the field from second line element in a symmetrical point that has also this electric field x component and the y component right there. Just take a look at the two components from two line segments. the x components of these two vectors are aligning in the same direction, so you should add them together. But y component of those two vectors are completely opposite direction, but the same magnitude. So they cancel out each other. So that leaves only x components. So if you integrate all the field vectors out of this line charge, only leaves the x component. There should be the no y component. So that's why you only have electric field that x component.
Okay. So this is also similar with the what we solved the sample problem 22.01 because this arc is symmetrically distributed in arc. So basically not this one. Where is it? Okay. This arc. So the one half of this arc located in the positive y direction, the y-axis, and half of that in the negative y-axis. So that the field out of those two positive and negative portion produce the electric field in y-axis too, but they're opposite directions, so they cancel out each other when you leave the x component. Just like the previous problem we already discussed. So that if you have symmetrically aligned line charge or any type of actually symmetrical shape, produce the electric field in one direction, probably in the x-axis in this kind of problem. So there's no net electric field in vertical direction out of the symmetrically distributed line charges, or maybe like even spherically actually distribute the surface charges too. So that is the probably if we have still time the next week, I quickly just go over the last problem, but this is end of the today. Do you have any question regarding any part of these problems?
No, I think all the problems were pretty similar, so I think
Yeah.
I got a understanding of it at the end. Yeah.
Okay, all right. So as I said, I'm gonna upload the files and video in your account, and if you need it, you can take a look back and then just review the problem yourself. Again, if you have any question regarding your quizzes in this Friday, then just feel free to email me. I'll take a look
Okay.
and get back to you. All right.
Gotcha. Thank
Otherwise,
you.
I'll see you next week.
Bye.
Bye.